So yesterday we have seen this Parzen window problem where two classes were given to us, say like this, n equal to 20 and 2 equal to 11. So there were 31 samples given to us, and we were asked to find out what is class for x test equal to 3.1. So what we did, we took the window sides h equal to 1, and then we put window around this 3.1 for omega 1, and then we find out how many samples of omega 1 do fall in this window. So there are 6 out of say 31. So there were 3, I think. Yeah, 3 out of 30, 3 out of this 20. Okay, so we got 36 by 31, and then we just repeat the procedure for omega 2, and then we find that this is greater than the second one. So my class is omega 1. So this was the Parzen window method. Now the effect of Parzen window is totally dependent on the size h. If you take a small size, so if you take a small size, you will see that finer and finer boundaries are captured for this two class problem. So these reds are say omega 1 and black dots are omega 2, and the boundary which is the decision boundary uh, due to this Parzen window approach is given here. Here h is small, so this is small h and this is big H. So when you take big H, the edges formed due to this Parzen are quite smooth, and they are not capturing the variations, high variations here. Okay, so there is a mixture, good amount of mixture of two classes here, so which is not captured by high value of H. When you take small value of H, this portion is probably getting more accurate boundaries. But when you see downside, here the spread is uh, of the samples is good one, where this kind of boundary is required. So when you take small h, the boundary created here is not that generalized, but here the boundary is in a better position and it is more generalized. That means this is capturing the essence of samples more correctly than these boundaries. Okay, so there are many variations here and there are less variations here, and you see this red and black portion is properly classified. So there must be a trade-off on user has to decide this value of h depending on the situation and depending on some trial and error method. So you start with some value of h, you find out the performance of system, and then you can change the value of h as per the requirement. So that is about the Parzen, but we will now move to the next point that is called as probabilistic neural network, which is the parallel implementation of Parzen window. So this is kind of a neural network implementation of a Parzen window. So what we are trying to do is we are trying to make a system or a circuit, say like this, which will take the input x and it will directly give you output for different classes, say omega 1, omega 2, up to omega say c. Then you choose the category for given input for which you get largest output. So that is how this will work. Now to build this circuit, we are going to use the concepts of Parzen window. Okay. Now you can see there are 3 layers. First one is input, the second one is pattern layer, and the third one is the category layer. Now what is done is at the input side, you can see here there is node x1, x2 up to xt. So where d is small d is the dimension of input. So if I write capital X, then this capital X consists of d values. Okay, so they are x1, x2, x3 up to xd. So they are here. Okay, now this input, this complete input is called as x, is given to all the nodes here. Okay, so 1, 2, 3 up to n. So when you are provided n samples in a Parzen window problem, say total number of samples are n, then you will create n different nodes in this layer. Okay, each node is representing one sample. That means, suppose my training data is equal to suppose x1, x2, and up to xn. So there are n samples, and there are suppose C categories. So this data here, say x1 belongs to some omega I, x2 belong to say omega 1, and so on, xn belongs to omega c. So each input is provided with a label, that is its class. So x1 is omega I, x2 is omega 1, x3 is omega 2, and so on. Okay, so this sequence may be random, so uh, there is no situation that x1 will belong to omega 1, x2 will belong to omega 2. Anybody can belong to any class. So it's a mixture of samples belonging to C different classes. Okay, so the last layer you see is representing categories. So categories are omega 1, omega 2 up to omega C. Okay, so I hope you got this point. X stands for input. Okay, and then you are provided n number of training samples, and each node here represents one training sample. Input nodes, that is x1 to xd, everybody is connected to each node here. Okay, so all nodes are receiving input x. Okay, so everybody is receiving input x. Say this middle layer you can call as pattern layer or a neuron layer. Okay, so there will be one activation function for this node that we will discuss in next slide. Now one more thing, suppose I choose any node here. Suppose I choose this node. So this is representing suppose pattern x1, and you will see that there is connection from this node to omega c. So there is a connection. So this will be a connection from first node to omega c node. It means that omega x1 belongs to category omega c. If it is the case, then and then only there will be a connection. Now I take some second example. Suppose this is x2 residing over here is connected to omega 1 like this. This will be done only when x2 belongs to omega 1. Okay. Now like that, x3 is belonging to omega c and this xn belongs to omega 2. So you have to remember that you will connect the connection between a pattern node to category node only when that particular pattern belongs to the respective class. Okay, so otherwise there won't be any connection. So there is no connection from say this x1 to omega 1. So this connection do not exist. Why? Because x1 is belonging to omega c, so there is no connection here. Okay, so like that this circuit is constructed. Now the next step is to find out the weights for this connections. So that is called as W matrix. Now why this is there, we will see. So this is the same diagram. Only thing is that this is the activation function for each node called as pattern node. So input is suppose X test here is received here by pattern X1 and it is compared with X test. So X test and X1 they are compared and actually they are compared such that whether the pattern is falling in the box or not, because we are implementing the Parzen window. So these are all representations of different windows. Now the activation function residing here is this equation, suppose 1, which is e to the power 1 over sigma square into net minus 1. So why this is coming, we will see. Now before I move further, you must understand that we are implementing Parzen. So we are implementing Parzen for all C categories at a time. If you remember the earlier problem, to differentiate between omega 1 and omega 2, what we did, we took the samples of omega 1, we fit a window around the X test and then see how many samples do fall into that, and then we divide by total number of samples and then we proceed to find out the probability for that particular class. Then we go for second class and then we repeat the procedure. Finally we decide or we take a decision regarding X test depending on who is having the largest probability. So we are implementing finally Bayes, but in a different way. We are now what we are doing is we are doing same thing. We are making a circuit which will implement Parzen. It will give you answer in one go. So what we are trying to do is we are applying here X test. So that will be input. It will be processed through all these nodes and immediately we will get output directly on these category nodes. Okay. Now we assume that we are using a window which is a normal distribution kind of window or a Gaussian window. So instead of a pure rectangular window that we have seen earlier, now I am proposing to use a normal distribution window. So all these nodes, pattern nodes, they will implement a normal distribution window. So their activation function is a normal distribution equation. So that I am saying it is approximately like this. So we are skipping 1 over 2 pi, square root 2 pi and so on, which I can write here for a normal distribution or normal function. So I'm just skipping that. So I will not equate to that. I will just say this is approximately same. Now let us write, instead of x test, just say x, so that it will be simplified further, and you expand this product. So this x test is input, xi stands for training pattern, ith training pattern. So we will take one example so that these things are more clear later. So if I expand this bracket, this will be the product. So this is actually, I should write x minus xi transpose multiplied by x minus xi. So I'm just expanding here. So it will be x transpose x plus xi transpose xi minus twice x transpose xi. Now next thing is I normalize x and xi. So if we normalize input and training pattern, then this x transpose x will be equal to 1 and xi transpose xi will be also equal to 1. So these are norm squares. So norm is the length of the vector. So when you normalize, length of the vector becomes 1. So their square is also 1. So if you don't remember this, you can note down. If I take vector A transpose A, this is called as norm of vector square. And norm of vector is nothing but length. If length of a vector is 1, then it is called as normalized vector. So this basic you keep in mind. So I can replace this and this by 1. So I am writing here, and this will be as it is. So this 2 gets common, and if I take it out, then this will be cancelling with this. Okay, so finally I get this. Now what I'm going to do is this xi I will call as weight of the connection. So xi we will call it as wi. So just name change, and this minus we can take inside. So if you do that, then this will be reducing to this form where net is nothing but x transpose wi. So we will call this x transpose wi as net, that is net input going to the neuron. Now if I go back here, and I take out some node, say if I take out node number 1, say this node 1, if I draw here, so there is some activation function and it is receiving input x1, x2 up to xd. So this is the input pattern x, which is to be classified. So this is received by this node. Okay, so this node is due to the pattern x1 and it is connected further to some omega I or omega c in this case. So I will write here omega c. Now the weights that we have discussed in next slide was discussing the importance of this connection, this connection, this connection, and this connection. So this will be having its importance omega, say W1, this will be W2, and this will be WT. Okay, and we said that Xi is Wi. That means the training pattern X1 will be W1. So if I say X1 is equal to X11, then X12, so on up to X1D. Okay, so this W1, small W1 will be equal to this X11. So what X11 stands for? X11 stands for the first value of capital X1. X12 stands for the second value for pattern X2 and so on. So this whole thing is actually X1 normalized and input is also normalized. So input here is normalized and what is residing here as the weight is, suppose this is x1 normalized, xn normalized, this will be x1 normalized, this will be x2 normalized, x3 normalized, and so on. Now what a neuron or what this pattern node receiving is called as net value. So this net value which is received at each node at each pattern node is called as net, which we said that it will be X transpose Wi. Okay, for ith node, net value is net I, which is equal to say X transpose Wi. So where X is our input, so which is already normalized. So this is also normalized. Okay, so if that is the case, then this net will be placed here in this equation and output. So this will be equal to output of the neuron or pattern node. Okay, so this is the activation and that will be governing the output of that node. Now what we do finally is we add the inputs which are coming here to the category node, suppose there are inputs like this, they are coming, so they will all produce some output due to the input. So we will do the summation here. So meaning is we are having different windows here. We are creating different windows here. Say like this. So whenever the input falls in these windows, if it is falling in this window, it will produce some output. Okay, so if it is producing some output, all such outputs we are going to sum, and that will be the final outcome of that category. So let us see the training algorithm of this PNN. So normalize each pattern so that its length is 1. Place the first training pattern on input units. Set the weights linking to the input units and the first pattern unit such that W1 is equal to X1. Make a single connection from the first unit to the input unit corresponding to the known class of the pattern. Say it means that this is your input X. You create first node here due to the pattern X1, and these are your output nodes. Say omega 1 to omega C. You just connect depending on the class of this X1. You connect output of this node to the respective omega C. Okay, so then we repeat this procedure for all the training samples. So you will create now second node due to X2, and you will assign the weights here equal to X2 for this particular connection, and you connect it to the respective category. So like that you will build the circuit. So this is talking about the construction in the algorithmic way. Now once you build this circuit, we need to use it. Okay, so the input patterns which are unknown. Now what we do, we normalize the test pattern, the unknown pattern. We compute net for each node, each pattern node. Then we pass on this net through the activation function, and then we do this sum procedure. We add all the contributions from all pattern units connected to that particular output node. So this is similar to Parzen or inspired from Parzen. So we have one window implemented here. So this is nothing but a window which checks whether you are inside this window or not. If you are inside this window, you will get some output. If you are outside, your output is very small. Okay, so how many such training patterns do support the applied input will give you the probability. Okay, so from likelihood we can estimate the posterior. So that is what this Parzen is doing. So we will stick to the maximum value of this thing. So this is talking about the same. I hope I should take one example so that things will be more clear. So you can note down this problem. Design a PNN. Design a PNN using following training data. The first part is assume the variance equal to 1. So this is the variance for that window. So this variance will decide the width of the window. Say I am having a Gaussian distribution. So this is sigma square equal to 1 window suppose, and I can have sigma square equal to 2, then I will have a bigger window. So maybe like this. So depending on the width, your spread will increase. Let us say sigma square equal to 1, and I have 4 training samples. 2 belong to omega 1, 2 belonging to omega 2. Okay, the question is classify X test 2.5, 2.5. Now let us start designing this PNN. First thing is to normalize the training data and test data. So I take this omega 1 set, this one, and I take the first training sample 1 1. So normalization is like this. So 1 1 will get multiplied by this 1 over root 2, because I need to divide this vector by its length so that it will be normalized. So length of 1 1 is 1 square plus 1 square square root. Okay, so this is my current length, or this is norm of x1. So if I divide this x1 by its norm, it will be x1 normalized. So this step is doing that. So this is the length. I am dividing by length to this x1. So it will be x1 normalized. Similarly, I go for x2. So x2 is 2, 3. So 2 square plus uh, 3 square. So it will be 4 plus 9. So square root 13. So I should divide by square root 13 so that I will get x2 normalized. Then similarly, x3 normalized is 1 by root 13 multiplied by 3. So it will be normalized. Then x4 is normalized. Now these 4 patterns are normalized. Similarly, we will normalize X test. So 2.5, 2.5 was my test sample which is to be classified. So 2.5 square plus 2.5 square. So I think 12.5, and square root of that. That will be length of this vector. So you can divide by that length. Now you see, this is the diagram. So there are 2 dimensions here. So all the patterns x1, x2, x3, x4 and x test, they are all 2-dimensional. So we will create 2 nodes here called as x1 and x2. So you will connect your input here. That should be normalized. So we are done with this step. Now there are 4 patterns, training patterns given to us. So we will create 4 nodes here. Each node is x1, x2, x3, x4. Due to these 4 patterns, we are creating 4 nodes. Now each node will receive these 2 inputs. So you have to have connection here, here, and here. Now see carefully. So the connection from small x1 to capital X1 and small x2 to capital X1, say these 2 connections, are having this weights 1 by root 2 and 1 by root 2 due to this first training sample. So first training sample was 1 1. Its normalized form is 1 over root 2 1 over root 2. Okay, so this will be my weight vector for node number 1. So you will write this 1 over root 2 here and 1 over root 2 here. Then you will take the second pattern and the connections going to the second pattern, they will have this their respective weights 2 over root 13 and 3 over root 13. So where you will write that? So you will write here 2 over root 13 and 3 over root 13. So like that you will construct whole this diagram. So we can write whole this connection in a matrix form like this. So this is sample x1 normalized, this is sample x2 normalized, this is x3 normalized, and this is x4 normalized. So you will keep the patterns, normalized patterns in a row. So this x1 and corresponding weights 1 over root 2 and 1 over root 2 you will find as row number 1. The weights of second node you will find as entry in row number 2. So this constructed matrix is called as weight matrix. Now what is to be done? So this is the design actually. So designing is over and you will see that since x1 belongs to omega 1, there is a connection here. Then x2 belongs to omega 1, there is a connection here. x3 belongs to omega 2, so I made a connection here. x4 belongs to omega 2, so there is connection here. So there is no connection from x1 to w2. Why? Because x1 belongs to omega 1, so there will be connection respectively. There won't be connection for omega 2. Similarly, there is no connection say from x3 to omega 1, since x3 belongs to omega 2, so this connection do not exist. So once the designing is over, we want to now classify the given test sample. So first step is to find out the W transpose or W into X test. So if I multiply by X test here, you will see that this row gets multiplied with this column, this row gets multiplied with this column. So you will get net 1, net 2, net 3, net 4 immediately. So in one step you will get the nets of all the pattern nodes. So I just substitute here the input which is test input x test. So immediately I get the net of each node. So net means I am talking about the net value which is going to this node. Okay, so we are not calculated output yet, so we will calculate now output. The output of each node is given by this formula. Output is equal to e to the power net minus 1 divided by sigma square. Now sigma square, I think we took it as 1. So for sigma square equal to 1, if I substitute the corresponding net values for each node. So for node number 1, this is 1. So this net is 1 here. So 1 minus 1 divided by sigma square is 1. So this will be equal to 1. So if I take now second net value, so 0.98 minus 1 divided by 1. So this is 0.98. For third, this is 0.98. For fourth, it is 0.99. Now next type is to find out the final output. Now we have four outputs due to four nodes. So we obtain the outputs here for each node. Then we need to sum the outputs. So for W1, we need to add O1, or say for omega 1, we need to add O1 plus O2 because O1, O2 belongs to omega 1. For omega 2, we need to add O3 and O4. So we add this, we found that 1.98 is greater than 1.97. So decision is omega 1. Okay, so this is how the Parzen parallel implementation works, called as PNN. Okay, now as a homework, you take sigma square equal to 2 and find out the result. What happens to this result? Use exactly same steps. Okay, I will put this video. You can go through it once again and try to solve this. So let us stop today.